So in the last problem, in part A, we have to look at the diagram and figure out whether the precession is clockwise or counterclockwise. Note that the weight from the top point of view is into the page. The distance from the gyroscope to the pivot point is to the left, so we can say R is to the left. Excuse me. And so the torque, let's call this W. The torque is, remember, the cross between the distance and the weight, in this case, the force. And this will be directed, if we use the right hand rule, to the left into the page. It would be toward top of page. So if that is the case, that will imply that the precession has to be clockwise. In order for all of these conditions to be true, the precession has to be clockwise. Let's denote precession, angular speed, by omega is 1 revolutions for every 4 seconds. So this is the same as saying 2 pi radians over 4 seconds, which gives us about 1.57 radians per second. Weight is little mg. So if we use the sum of the torques equals I alpha, where we can say that instead of using I alpha, let's use the definition of what omega is. Omega is the torque over the linear angular momentum. So that's the weight times the distance over I omega. And from here we can say that omega equals WR over I capital omega, and the weight we know is mg. R, I is 1/2 LM big R squared times omega. And now we can say that the angular velocity is this 1/2 turns to the top, it becomes 2 times the mass the masses cancel, right? So times 9.8 meters per second squared, that's G, times R, which is 2 centimeters, or 2 times 10 to the minus 2 meters, divided by capital R, which is 3 centimeters squared times omega, capital omega, which is 1.57 radians per second. We do that, we get about 280 radians per second, which if we want to change to revolutions, multiply that by 2 pi radians for 1 revolution. Multiply this by 16